What I'm going to focus on is state of charge, more importantly state of health measurements for lithium cells, battery packs. I'm going to focus this primarily towards the automotive industry because this presentation is in direct response to a lot of conversations I've had over the years with car companies, particularly in Germany. And this was in response to some of their requirements or their suggestions or their wants and needs. So what I'm going to do is going to frame a particular problem faced in the automotive sector and then try and determine how we can use impedance spectroscopy as potentially a methodology and a tool to overcome some of those issues. So I'm going to focus primarily on state of charge and state of health. You'll see SOC and SOH written a lot, state of charge, state of health respectively. Now, we get this the right way around. Okay. In terms of the industrial requirements, I'm going to frame the problem. And the problem is this. When you buy a new car, sometimes the car goes wrong within the first year, and that's covered by warranty. And the car companies don't like warranty returns. It creates a bad impression about the car, and it costs money. And so what they find was that 70% of first-year warranty returns were reported as a battery problem. So this was for your typical automotive car. This is a lead-acid battery. But clearly they've got concerns that if you've got a battery problem in a well-established technology, lead acid, what's going to happen if we move to hybrid and full electric vehicles? We're going to potentially have a lot of warranty return issues. So what they found was that 70% of warranty returns that were reported as being a battery issue had nothing to do with the battery whatsoever. There was something else within the system. So they were spending a lot of time, a lot of money looking for faults within a battery, and the instruments they were using was just not giving them the precision and the resolution required to determine if it was the battery at fault or something else in the car. So they said, please John, can you help us come up with a methodology and a tool to help us resolve this warranty return issue? And I said, I'd like to help you, but I'm an instrument manufacturer, not a consultant. But anyway, I went back to my lab and thought about this and looked at the literature and was quite surprised in the state of literature. So I'm going to focus primarily on things like lithium iron phosphate because that's the material of choice, or it seems to be the material of choice for electric vehicles. And I'm interested in, if I look at a battery value chain, every part of this chain represents an increase in value. So this goes from basic research and development all the way through to end user appliance, systems integration, and maintenance, service and support. So I'm going to focus on the end user systems integrator. The systems integrator is the car company, and the maintenance support is your local workshop that's going to fix your battery and fix your vehicle. And I'm going to skip through a lot of these slides because of time constraints today. But this is one of the next important slides. So requirements. What we need in the automotive sector is firstly a reliable method to determine the state of charge. As Rob said, this is the indicator on your dashboard that tells you how many miles you've got left or how many kilometers you have left between your next charge. So you need to be able to determine that accuracy. That makes sense. You don't want to be breaking down on the hard shoulder because your state of charge indicator is wildly inaccurate. So that's an obvious one. But in terms of warranty returns, what we need to be able to determine is something called the state of health of the battery. In other words, a snapshot of the projected lifetime of the battery, what condition the battery is in. Because it's this that can determine the warranty return rate. Now what manufacturers need specifically is they need to be able to determine the state of health of the battery within that warranty period. Now that warranty period would be 1 year. And typically speaking, the battery is at 90% state of health after 1 year. So a new battery, a 1-year-old battery, is a pretty healthy battery. But it's very difficult to provide a high resolution measurement technique to tell you it's a healthy battery. Most measurement techniques will tell you it's a okay battery or it's a healthy battery, but it can't resolve whether it's okay or it's really healthy. All it can do generally is tell you when it's bad, when it's really bad. Well, you already have a feedback mechanism when it's really bad because the car never starts. So we need tools that can precisely determine the state of health battery when it's in its early use period or its early warranty period. So there are various techniques that have been developed, but they're generally at an early stage of development. And one of the techniques that I'm going to focus on, of course, is impedance spectroscopy. And review of the literature showed that the research in this area stalled effectively as the research money fled away from battery research in the early 2000s, all to fuel cell research. And ironically, it's come back full circle. So now the money and the development is focused towards battery research. But in terms of state of health development, diagnostic tools using impedance spectroscopy, there's remarkably little literature in comparison to the needs of the industry. But furthermore, the other techniques for determining state of health are still at a basic level. So there's a drive to resolve this problem, but there's relatively little work in comparison to the scale of the problem. So that's what I'm going to focus on. Okay, I'm not going to talk about speed of measurement. This is a nice follow-on in terms of how you would implement something in an industrial sense, but I'm going to focus straight on, firstly, developing an equivalent circuit model for state of charge, and then using that equivalent circuit model to see if I can then extend that to determine the state of health of a battery. So this is some work that was done actually in the UK. This is at the University of Oxford and Imperial College. And so this is on a prismatic cell at various states of discharge. And these are the measurement parameters, 250 milliamp AC stimulus, and that's the frequency range. And the important thing is what they've done is they've discharged the cell to various states of discharge. So clearly 100% state of charge is a fully charged battery, 0% state of charge is a fully discharged battery. Now, you don't have to be an expert in impedance spectroscopy to see that there is a difference. So as we go from fully charged to partially discharged to fully discharged, we see a marked change in the impedance spectrum. That's quite nice. So they then went on to develop this generic model. Now there are different models that are developed in the literature, but if you study them in a little bit more detail, they essentially amount to the same thing. And so what we have here at high frequency, we have inductance, and I'll talk about inductance on our group sessions this afternoon. But the first interesting parameter, as Rob said, is the series resistance. So this is our ohmic resistance in the cell, something we want to reduce. And then we have something called these time constants, where we have resistors and capacitors. In this case, it's something a little bit more complex than a capacitor, but for now we'll say it's a capacitor in parallel. And these parallel combinations of R and C produce our semicircles that we see here. That black one's quite a nice one to show. And then we have two of those, one associated with the solid electrolyte interface, and one associated with the double layer. And then we have something in the end called a Warwick impedance, and a Warwick impedance, for the electrochemists amongst you, is associated with a diffusion. So this is diffusion of ionic species within an electrolyte. So there's our nice simple model. And if we simulate this is the response we get. So this is a real simulation of something I did in software back in my office. So this is an equivalence of the previous circuit, and this is the simulated response. So it looks pretty similar to the measure response from the paper by Howey et al. And there's nothing like simulation comparing it with real data. So this is real data of a lithium cell using the Modulab XM that you see in front of you. And what we have is the red line is the real data, and the blue line is the fit. So I've got an excellent correlation between a measurement and the model. So I'm happy. I've got a model now that can be used to fit data or model the electrochemical properties of my battery. So that's the first statement. I've got a model. Now what can I do with this model to give me something useful? Well, in terms of state of charge, and this is again from Howey et al., so I'm not claiming anything here that is not already known or rehearsed in the literature. What they did is they plotted the impedance of various circuits within that model and correlated that to the state of charge of the battery. So what we have here is the impedance of a particular element and the state of charge. And we can see for the solid electrolyte interface element, we can see a correlation between the impedance as a function of state of charge. And the charge transfer resistance is a correlation between the impedance and the state of charge. Now this is very good, the resolution is good at, as we discharge the cell to larger and larger values, but we can see that in the early stages of the discharge cycle, the state of charge resolution, in other words, the difference between say a battery that's fully charged and a battery that's partially discharged, there's some effort required in terms of improving that resolution. And that's where things like the accuracy of your measurement system really become very important, because you need a measurement tool that can resolve the difference between, for example, your SEI and charge transfer resistance between 100% state of charge and 75% state of charge. So that comes down to the accuracy of the measurement system. But the first thing to say then is, the next thing to say is, we do see a good correlation between impedance measurement values for different elements as a function of state of charge, particularly as we decrease the state of charge. So what this is telling us is we can use impedance as a tool, potentially, to give us feedback in terms of the battery life between charges as we get closer to the full discharge. Okay, so this is a state of charge test that I did. Again, I wanted to verify the model and verify the work. And I see again a correlation this time between, rather than looking at a particular element, I just looked at a particular frequency. And in this case, I got much better resolution between the impedance response and the state of charge at these high values of state of charge. So we could resolve the state of charge by just measuring the impedance at 50 millihertz. So this is in the diffusion regime of the impedance curve. So we'd use diffusion as a method to determine the state of charge of the battery. Okay, that's state of charge then. To conclusion. We can use the EIS measurements at 50 millihertz to determine the state of charge. That's simple. Next problem, we're going to determine what the state of health is. And this is the thing that's much more complicated. So my definition of state of health, for the purposes of today's, is we're going to compare the capacity of the battery at cycle 1 versus the capacity of the battery at cycle n in percent. So, what's happened with the state of health measurements in the literature? And this is not a complete review, this is just to give you an indication of some of the work that's going on. So, this is another group, I believe, based in Newcastle. They try to monitor the state of health of the battery as a function of the equivalent series resistance. Now this would be a lovely tool if it were true, or applicable across all cases, because that would be a very simple measurement. And so what this showed is they had a correlation between the ESR measurement and the state of health. But I said at the beginning, the car companies need the ability to resolve the state of health of the battery when the battery is relatively new, so that they avoid this warranty return issue. So we need a higher resolution method or methodology to be able to determine how the impedance can change as a function of state of health between 100 and 80% state of health of the battery. You can clearly see here that these points are probably within the noise of the measurement system, and therefore the differentiation between 100% state of health and 80% state of health is questionable. That's not the resolution that's required in industry. We need something with higher resolution. So the last minute, this is what I did. Okay, so I looked at the state of health as a function of frequency, and I recorded the impedance spectra at a different range of measurement cycles. So for 20, 60, 160, 260 cycles at a 60% state of charge measurement point. Comment. Clearly, we can see as we increase the number of cycles, as we age the battery, we see certainly there's a difference in the impedance spectrum. That shows you there's a difference, but it doesn't allow you to quantify what the difference is. So, what did I do? I took that data, noted that in the previous slide we had a 2-time constant model. If we have time constants where the values of R and C respectively are similar, such that the ratio of R1, C1, R2, C2 is 1, your 2-time constants in your Nyquist plot condense to a single time constant. So you have one apparent time constant. Okay, so now, can I find an empirical relationship between this model, which is essentially a simplified version of the previous model I showed you? Is there an empirical relationship between this and the state of health of the battery? And there is. Quite nice. What we've got here, this is the time constant in seconds of that parallel RC system. So from my impedance data, I determined the RC and then plotted it versus the state of health. And what I found was, and this is the conclusion, if we measure the impedance of the battery at low state of charge, i.e. towards the end of its useful operating range between cycles, so basically discharging the battery close to 100% discharge, and measure its impedance at that point, we can provide a resolution technique that can determine the point at which the battery is operating at 90% state of health. And this is the resolution that's required in the automotive sector. So what we have here, this is the RC constant at various different states of charge. And we can see that as we approach full discharge of the battery, I can resolve the state of health very nicely using the simple time constant as my diagnostic tool. How will this apply in the automotive sector? You have a battery, big battery pack, you measure the impedance. There's a trick on how we can measure the impedance using the battery itself as the load for the impedance analyzer. Measure the impedance close to the point at which the battery is fully discharged. So you just take your battery into your local garage, they discharge the battery, they measure its impedance, they analyze the RC constant using an automated process, and they look at the value of RC and go, oh, well, it's giving me a value of 0.2, and they look across on this graph, oh, it's about 42% state of health. 50% I want to throw the battery away anyway. So we could use this as a fairly simple diagnostic tool to determine the state of health of a battery in situ. That's what I want to say about that today.
Thank you very much.